Hello everyone, today we are going to tell you about our RL approach for the adaptive speed regulation on a metallurgical pickling line. I'm Boris Voskresenskii, Chief Digital Officer of Severstal.
My name is Kseniia Kingsep, and I'm Head of Data Science.
And my name is Bogomolova, and I'm Data Science Team Lead.
Okay, let's go to the purpose of metallurgical pickling line. After hot rolling process, you usually have some defects on your steel, such as scale, and you should remove these defects from the surface of your steel. So you are using pickling process to remove it. And metallurgical pickling line, it is a line where you pull your metal strips through acid bath to remove these defects. Let's go to our unit. I want to show you some video with it. It is quite big unit with production of more than 1 million tons per year. Here, for example, you can see loopers of this unit. You can't see acid baths here because they are hidden. And here our interface of our model. As you can see, there are many parts of this unit, but we control the central part of it for now. And here you can see our product. Again, one of the looper of the unit. In the next slide, I will tell you about this machine with more details. And now, metallurgical pickling line overview. There are 3 transport units here. First transport unit, there you weld your coils to one big strip, because your metal should be continuously go through pickling bath. Then second transport unit, where your metal is pulling through acid. And the third transport unit, where you cut your metal into the final product. And there are 2 loopers. The first looper, you use it for storing of metal when you are not weld your coils, and when welding process is going, you use this metal to pull it through pickling bath. And the second looper should be empty enough to have time to cut your strip in the sheet blades. So the main reason of loopers is to continuously pull your metal through pickling bath without stops. If you stop your metal in pickling bath, you can produce some defects in it. let's go to the problem formulation. We have main parameters here. Firstly, it is time of the first transport unit. It is uncoiling time plus welding time, and there is time of the third transport unit. It is decoiling time plus cutting time. We should not go with higher speed than it is required by quality of our products. So we should monitor what type of metal is now in the second transport unit, and when we set our speed, it is the speed should not be higher than minimum of these required speeds. As for constraints, it is what I told you in the previous slide. So your first looper should have enough metal in the time of the first transport unit, and your second looper should be empty enough for the time of the third transport unit. And our main objective function, it is how much metal we can produce. So we should maximize sum of speeds of the second transport unit, or it is equivalent of minimizing of production times of our rolls. Let's talk shortly about the learning architecture of our solution. We have our environment where which is generating states of and rewards of our unit, and reinforcement learning agent plus analytical agent are working together to produce action. In our case, the action is the speed of the second transport unit. My colleagues will tell you about this process with more details. So let's tell you shortly about our technology stack. We have direct control of our unit with this solution. So we communicate with our unit through UA server, and from UA server we take pickling line state. Our Java application sent this state to the Kafka, and our application in Python, which is working in a Docker container in Kubernetes, sent to the Kafka action, the action of our agent. And again, Java consumer takes this information from Kafka and sends this action to the UA server. So this flow is working every second, and we can control our unit through it.
I will tell you about main components of our solution and walk you through the evolution of our RL approach. As you have seen before, one of the main building blocks for the whole training environment was a generative adversarial network. Why do we ever need it? We supposed beforehand that we would train a batch of different agents and they'd be data hungry. When we assessed the amount of historical data available, it became clear that it will not be enough to conduct all the anticipated experiments. We explored options to increase the amount of data. There are basically two ways: either augment real data or generate fake data. We have chosen to generate data because it gives access to an inexhaustible data set. Now, how the data looks like. Actually, it's a sequence of still strips passing through the pickling line. They are carefully put into a queue by planning specialists. Each strip has a set of parameters. Still strips are organized in groups with the same characteristics. Group size can vary from 1 to roughly 40, and we can consider strips identical inside a group except for the length. Moreover, planners take into account width and thickness, a difference between adjacent groups. When creating a queue, it's important because not all strips can be paired together. Within a group, strips share width and thickness and are 100% compatible. However, for different groups, it is not true. Also, the features of the strips, namely coiling temperature, width, and thickness, define the maximum possible speed of pickling and determine times of several technological processes on the pickling line. By now, it should be clear that we needed to generate tabular data, which at the same time has sequential properties. We broke a task into two subtasks. Firstly, we generated a categorical parameter, still grade. It's a high-level feature that comprises many characteristics of a group of strips. A natural way to generate such a parameter is to see it as a text generation task. Final model included a single LSTM layer and a dropout layer. Also, like in text generation tasks, we introduced a special end token to indicate an end of a group of strips. This measure helped to separate consequent batches of strips with the same still grade. Secondly, to enrich our group of strips with appropriate numeric parameters, we created a conditional gun using still grades as a parameter to condition the desired output on. The architecture of a gun includes two neural networks, a generator and a discriminator, who compete with each other, playing a minimax game. The main idea here is to use supervised learning in assistance to unsupervised learning. A generator receives a categorical parameter, still grade, and a random noise, denoted by Z. Then the generator tries to produce some fake data, which is afterwards fed to the discriminator along with the real data. The aim of the discriminator is to distinguish between fake and real data. As the generator is getting feedback from the discriminator, it starts to generate more and more acceptable samples. The discriminator is trained such as to minimize cross-entropy loss, and the generator's weights are updated to increase the logarithm of the probability to classify fake samples as real ones. There are some tricks that proved useful in our approach. First, we used Gaussian noise as initial input to the gun. Then we used label smoothing. We labeled our samples not by zeros and ones, but by float numbers close to 0 and 1. Also, we trained the discriminator for 5 steps per one generator step. It helped to achieve faster learning. I think it's worth mentioning here that we generated sequences of fixed length according to our RL setting. We'll talk about it later. Now, let's proceed to the results. It's quite difficult to evaluate the quality of a gun, especially if we're not dealing with images. So, at first, we carefully monitored the training process that consisted of 2000 epochs to ensure that the generator gradually learns to fool the discriminator so that the latter is no more able to perform correct classification. Furthermore, we explored the sequences of strips that we generated to match the requirements of the planning specialists. Here you can see generated dataset compared to real data. Generated sequences of still strips then were used to train and validate RL agents, and historical data was used as a test set. The second building block of our solution is the kinematic environment. This is a digital twin of the pickling line that simulates the movement of the strip. Two main components here are the dynamic of the line itself, rules based on mechanics. This part was implemented through mathematical modeling. Second component is the disturbance that occurs because parameters of still strips affect several technological processes. And this part was done using probabilistic approach. I guess here finally starts the part everyone cares for, the RL details. Frankly speaking, RL is not widespread in real-life industrial applications yet. Therefore, before diving into complex experiments on an explicit kinematic environment, we decided to prove the concept in a simpler setting. You remember that the pickling line has two buffers, two loopers, acting as constraints to the whole system. At first, we have designed a simplified environment with only one looper to make the speed control task easier for an agent. Unlike the full-scale digital twin, it was almost a deterministic environment with some still strip parameters. Each training epoch consisted of 20 subsequent still strips. It is true for all our agents, in fact. So we have deliberately broken continuous tasks into a bunch of episodic tasks. We started with an agent that received environment state once in a second and took the decision to accelerate, decelerate, or keep the speed on the same level. The agent was fully independent and showed an ability to control the speed. However, the death rate was a bit higher compared to the simple baseline rule. By the death rate, I mean the proportion of epochs where an agent violated the constraints. Another major concern was frequent speed change that was not desirable due to quality and reliability requirements. The latter issue was overcome by introducing a penalty for speed change, but death rate is critical for the whole setting. We expected the difficulty to avoid deaths to rise with the complexity of the environment. Therefore, at this moment, it became clear that we needed to modify our approach to get more stability. So we came up with the idea to let an agent change the speed with respect to the baseline. This one of the crucial steps to success. Uh, to explain how we proceeded to the next step, let's recall the pickling line kinematics. Both first and third transport units have four clear stages of movement. Coloring for the stages of first transport unit are at the top of the graph, and for the third transport unit at the bottom. Let me show the stages on the example of the first transport unit. Its speed is shown here by a blue line, and the speed of the second transport unit is shown in orange. Recall that second transport unit is actually the one where we want to control the speed. The stages are acceleration, shown in green. Uh, at this stage, the speed of the first transport unit rises and exceeds the speed of the second transport unit. Then comes synchronization stage. It's shown in blue. It is the stage when the looper is full and the speeds become equal. Next stage, shown in yellow, is slow down, when the speed of the first transport unit decreases. This indicates the end of the steel strip. Last stage is pause, when the strip inside the unit almost doesn't move and the speed equals to 0. This stage is needed to weld or cut consequent strips. As these stages follow one another in the same order, one can break down the pickling line state into 16 unique combinations of first and third transport unit stages. Inspired by this fact, we created an agent that sets speeds once in a stage combination. This approach also coincides with the desire of the technologists to get a step-like speed graph, as it provides the better quality of steel. We tested this approach on a simplified two-looper environment. This environment also has more probabilistic parameters inside. Here we were pleased with the results, stated that the proof of concept was successful and started to integrate all of our full-scale building blocks together. The full probabilistic kinematic environment, a state initialization module, steel strips generated by GAN. To sum up, I want to mention the key ideas that led us to success. We used several RL agents to work consequently for the common result. One agent per stage combination, 16 agents in total, and cooperation with a mathematical baseline. This gave us more reliability. A thorough explanation of the RL algorithm we used and cooperation strategies we tried will be presented by the next speaker.
According to the general approach in RL framework, we separate 4 different settings. So it's a reward, action, a state, and policy evaluation strategy. At first, let's look at the reward function. We separate positive and negative rewards. So the positive reward associated with the boost in the speed of second transport unit suggested by the RL agent over the decision done by the base agent. So the negative reward arises from violation of the constraints. As it was already mentioned, by constraint, we consider the limit in the volume of the first or second looper. As soon as agent approaches this limit, it's accounted for the negative reward. Meanwhile, the crossing the limit results in the agent death and consecutive significant negative reward value. The state is the information what the agent evaluates at every particular time step. Here we consider the 4 main group parameters: the speed, the roll length, or much better, it's a length left to be unrolled or called in corresponding transport unit, first or third. We also considered such parameters as volume of the first and second looper and expected time left to the end of the welding stage. And the last setting is a policy evaluation strategy. For our purposes, we used a deep Q-learning algorithm with a neural network as an approximation function for the Q value. So we decided, as already Kseniia mentioned, we decided to build 16 separate neural network or describe the behavior of the agent at every stage combinations. Every neural network was consisted from fully connected nets architecture, we use ReLU activation and L1 regularizer for the inner layers and linear activation for the output layer with the action values in the range from 0 to 10. As it was mentioned, we decided to use two agents, analytical and rally agent, which act cooperatively. The analytical agent or the C agent, so it's stated for the conservative agent, is deduced as a mathematical solution of the problem. The solution accounts multiple safety requirements to the automation process and is used by us as a base solution. On the top of this base solution, we applied an RL agent. We considered two different approaches. The first approach, in our case, it's a F-corp agent, so it stays for fully cooperative agent. So this approach supposes that a RL agent and a base C agent act simultaneously at every stage combination changes. And also at every 30 seconds while this stage combination is keep going. At the same, and the cooperation exists at every stage combination. On the other side, in the second approach, so it's stated for the P-corp stage, P-corp agent here, and P-corp, what means is partially cooperative agent. So this approach supposes that the cooperation is active only for such stage combination where neither welding or cutting stage is present. When it's fair, two agents act simultaneously. Otherwise, the C agent is the only agent what decide what speed would be on the next time step. In the following decision, we'll compare the behavior of F-corp agent with P-corp agent and C agent. In this particular case, the C agent is the agent what acting every second. Likewise, it was implemented already in practice before we decided to develop an RL learning approach. On these two figures, on the left, the objective function is shown. So since we can formulate the objective function in two different fashions, the first one is the average speed per episode, and the second one is the sum of all speeds during this episode. Or in other words, it's distance what the whole steel stripes passing through the pickling line during this episode. So our box represents the distribution of values of speeds over the 200 episodes. Horizontal line as well as the sine value corresponds to the median values or 0.5 percentile. The most interesting results is both the excess of average speed median value and also scarcity of speed some medium of F-corp over the P-corp agent and C agent. So we attribute such behavior with excess of the death rate of F-corp agent. And we will try to describe it in more details on the next slide. So as I described on the previous slide, we allowed the C agent to act simultaneously with RL agent. Here, first two figures display the decisions made by two different type of decisions. One is the decision made by a cooperative agent, and another one is decision made by C agent in part of cooperative decision. So otherwise, it can be understood as a difference, that the difference between every pair of C agent and P agent or F corp agent would be the result would be a decision made by a REL agent. As it's seen in the most cases, the decision made by analytical agent determines the final action. However, for combination where the stage 2 is present, the RL agent become more active. So for the F-corp agent, the same is fair, but also for the 3 having stage combinations. So two having stages in this case could be understood as the stage combinations where the slowdown is happened, and 3 are having stage combination is the combinations where the welding or cutting is happened. And probably the presence of 3 having stages, the access and the speed for the 3 having stage combination for the F-corp agent results in an excess death rate of that agent. The bottom figures show the final result, the comparison of speed applied by 3 agents at different stage combinations. So, as a proof of the previous assumption, we observe similar excess of speed in having 2 stages for the P-corp and F-corp. And considering the higher death rate for the F-corp agent, we decided for the following implication to use a P-corp agent as our main agent. So we used only P-corp agent for the following within these two different approaches for the following implication practice. So in practice, we decided to exploit the advantages of both P-corp and C-agent and allow them to work at the stages where they display the biggest potential. So such strategy allowed us to break 4 records since May 2020 and resulted in productivity boost over 6.5%. So if you are interested in our research and would like to know some more details, you can take a look at the link here. So it's a link to our manuscript, what is published on Arxiv. So welcome and thank you for your attention.